In this video, we are going to apply Snell's law to the planar boundaries. Consider this figure. The refractive index in medium 1 is less than that of medium 2, or N1 is less than N2. On the other hand, Snell's law says N1 sine of theta 1 is equal to N2 sine of theta 2. So theta 1 must be greater than theta 2, otherwise Snell's law won't be satisfied. When theta 1 is greater than theta 2, the refracted or transmitted rays bend away from the boundary as you see in this figure. This is an example of external refraction. On the other hand, if N1 is greater than N2, then theta 1 is less than theta 2, and the refracted rays bend toward the boundary as you see. And that's why we call it internal refraction. Now, for internal refraction, we know that theta 1 is less than theta 2 as we saw in the previous slide, but if I increase theta 1, finally theta 2 reaches angle 90 degrees as you see here. This angle is 90 degrees, and that means that the refracted ray is parallel to the boundary. The corresponding theta 1 is shown by theta c, and it is called critical angle. We can easily find the critical angle by setting theta 2 equal 90 degrees in the Snell's law. Since sine of theta 2 is 1 when theta 2 is 90 degrees, we have this relation. Theta c is sine inverse of N2 over N1. If we still increase theta 1 to values greater than theta c, Snell's law cannot be satisfied. So no refraction occurs when theta 1 is greater than critical angle. And the boundary lies as a perfect mirror, and it totally reflects the incident ray as you see here. This is called total internal reflection. Be careful, this is total internal reflection, not refraction. Another optical device that is frequently used in labs is beam splitter. The beam splitter splits an incident ray into a reflected ray and a transmitted ray. We can also use it to combine two light rays into one. It's like a partially reflective mirror as shown in figure A. Figure B shows a thin glass plate, and figure C shows a beam splitter that is used for combining two weak light rays. And the output is a strong light ray. Another useful optical device is prism. The prism is mostly used for conducting the light ray in the direction we want. As we will see in the next chapters, the refractive index depends on the wavelength. So, if we shine the prism with a white light ray, which includes a spectrum of different wavelengths, then the angle of deviation is different for different colors or different wavelengths. Now, we want to make a relationship between the deviation angle theta d and the incident angle theta. As you see, theta d is the angle between the original incident ray and the exiting ray. This is theta d. Here I have formed two triangles For the lower triangle, I can write theta 1 plus theta 2 plus delta is 180 degrees. Also, theta d is an external angle for the upper triangle. This is upper triangle. One angle is beta, the other one is gamma, and this external angle is theta d. So I can write these relations. So I said that theta 1 plus theta 2 plus delta is 180 degrees, and also theta d is beta plus gamma. Also, look at the right angles shown by blue color. Let me come back to the previous slide. It is more visible. Here I have two right triangles, this one and this one. And if we consider these two triangles, the lower one is shown by angles theta 1, theta 2, and delta, and the other one is this, the big triangle. We see that this angle and this angle is 90 degrees. So I can conclude that delta plus alpha plus these two angles must be equal to 360 degrees. So I can conclude from that alpha plus delta is 180 degrees. From the first and third relations, we can conclude that alpha is equal to theta 1 plus theta 2. Because the first equation says that delta is 180 minus theta 1 minus theta 2. So I can substitute delta here and conclude that alpha is theta 1 plus theta 2. Now let me come back to the previous slide once again to show you two other relations. So here we see that angle beta is theta minus theta 1 because this angle is equal to theta. Similarly here, theta 2 plus gamma is equal to theta 3. So from these two, I can conclude that theta d, which is shown in this equation, beta plus gamma is equal to theta minus theta 1 plus theta 3 minus theta 2. But here we prove that theta 1 plus theta 2 is alpha. So I can replace here and obtain this relation. Theta d equals theta minus alpha plus theta 3. Okay, now we are going to apply Snell's law to two boundaries, the left boundary and the right boundary. The incident angle is theta, and the refraction angle for the second surface is theta 3. For this first surface, noticing that the refractive index outside is 1, I can write sine of theta over n is sine of theta 1. And for the second surface, I can write n times sine of theta 2, because the incident angle for the second surface is theta 2, is equal to sine of theta 3. The refractive index here is 1. But I can express theta 2 versus this equation, which is alpha minus theta 1, sine of alpha minus theta 1. So I can simplify this equation and write n times this bracket. I expand this relation, sine of alpha minus theta 1, as sine of alpha cosine theta 1 minus cosine alpha sine of theta 1. Noticing here that I have factored out n, I can simplify this relation like this. Sine of alpha times square root of 1 minus sine of theta squared over n minus cosine alpha times sine of theta over n. Now I can simplify further and write theta d equals this one. Theta d is this one, theta minus theta 1, or theta minus alpha plus theta 3. So I can keep these first two terms, theta minus alpha plus theta 3. Sine of theta 3 is this. So theta 3 is sine inverse of this equation. So I can simplify it further, and I've written that like this. Finally, let's briefly discuss the beam directors. An example is biprism or inverted prism, which is shown in figure A. We also have Fresnel biprism shown in figure B. We will talk more on that in the next chapters. Likewise, we have a cone-shaped device or axicon that converts ray into a collection of circularly symmetric rays directed toward its central axis in the form of a cone as shown in figure C. You can also see a real axicon on the right side. We will touch more on these devices in next chapters.